Alright, gang, here we go. So this is Chem 1, Unit 1, Part 2, States of Matter. Alright, so we're going to talk about states of matter. We're going to talk about physical and chemical changes. It'll be a nice short video here. Alright, so states of matter, solid, liquid, gas. You should be familiar with those. Okay, solids are defined by the fact that they have a definite shape and a definite volume. Okay, so whatever a solid is, whatever shape it is, however much space it takes up, that's defined. You don't expect a solid to change any of those states. And it has these states because the particles are packed closely together. Now, this is not a perfect representation, but like if you had if you were looking at the atomic level of a solid and you really zoomed in on all these things, then these atoms, this would be your solid, and these atoms would be all closely packed to one another, right on top of each other, and would not be able to move. Okay, and however much substance you had, that's what that's kind of how they're shaped, or that's how the molecules are packed close together. That's why there's no extra space between them. That's why you can't put your hand like through your desk. Okay. They're also not easily compressed. You can't take solid molecules and make them get closer together, because honestly there's just no space between them already. Okay, unless it's some sort of fancy one that has like a special crystalline structure as it freezes, like water. Right, now liquid, okay, liquids have a definite volume and an indefinite shape. So imagine you had a cup of water and you knew that had 50 milliliters of water in it, and you had that cup of water and then you poured it on the floor. How much water would you have? Well, you'd still have 50 milliliters because that's how much was in the container. The volume is going to remain constant, but what's its shape? Well, it's puddle shaped. It's a puddle shape on the ground as opposed to being cup shaped when it's in the cup. Does that make sense? You'd be really, really surprised if you poured out that cup and the water just stayed at cup shape sitting on the ground. Yeah? That doesn't make sense. Okay. Now, when you're looking at liquid molecules, the atoms in liquids, they look very similar to solids, except for they're a little less loosely packed than the solids are. And because of this, the atoms are able to move past each other. Okay, so imagine sand, in an hourglass, right? If you move that sand around, you can see the sand shift from one side to the other. The sand is what liquid molecules look like at the molecular level. Okay, obviously sand is a solid. It's just a lot of little pieces of sand. If you take liquid and you look at it at a molecular level, then those liquid molecules are kind of doing the same things that the sand bits are. Okay. Also, liquids, because they're still so close together, they're not easily compressed. They're going to take up a specific amount of space. There's going to be a little bit more space between them, but it's still really hard to compress a liquid. Now, gases, on the other hand, have totally different properties, and that's because they look very differently, right? And we'll spend a whole... Here, maybe I should label this for you. This is a liquid, right? And then this container, we'll say, has gas in it. Now, gas is very much spread out. Notice how I put my molecules way farther apart from each other than I did in the solid or the liquid. In fact, if you took a gas molecule and zoomed up, made it the size of a tennis ball, and said, all right, this tennis ball is my gas molecule, the next closest gas molecule on average would be about a football field away. In our air, just everyday air that you're breathing, there is vast amount of empty space in the air that you're breathing. Okay, you just can't tell because gas molecules and atoms in general are so impossibly tiny. Well, not impossibly tiny, but really, really tiny compared to us. So it doesn't feel like there's empty space. Like you wave your hand around and you can feel the wind. That's air molecules that you're hitting. Okay. All right, because there's so much empty space and they're not being held together by their intermolecular forces. We'll talk about that later. Okay, these gas molecules can fill the container they're in. So when you blow up a balloon, it's gonna fill that whole balloon up. Okay, and so these gases are just gonna constantly be hitting each other, run into each other. So these gas molecules are gonna be bouncing all over the place. Some of them are going to go up, some of them are going to go down, they're going to go all around. Imagine that it's just a bunch of little billiard balls that are bouncing into each other, running into walls, and so on and so forth. Now, because there's vast amount of empty space, these are easily compressed. Okay, easily compressed. That means we can take these things and force them down into be really tiny containers. That's why we can take gases like helium and hydrogen and propane and things like that and put them in containers. Okay, that we have a lot of it in just a tiny space. Now note, gases are not technically the same as vapors. Vapors are a liquid that's acting like a gas at a temperature that it should be a liquid. So like water vapor in the air, humidity, okay, that's technically it's a vapor, so it's a liquid that's acting like a gas when it really should be acting like a liquid. All right, that's how we've defined vapors. All right, and we can use the periodic table to distinguish all three. Okay, in this particular periodic table, the blue ones are the gases, the yellows are the solids, and the reds are the liquids. Notice that there's only 2 liquid elements. Okay, now this is at room temperature. Okay, the elements, it could all be liquid. You just have to get to a high enough temperature. All right. So, and they could all be solid, but you'd have to get them just to a cold enough temperature. Okay. So gases are the blue ones. Notice that there's most of the gases are on the far right, and then the right column with the noble gases, and then you got hydrogen in the top left, and then mercury. That's Hg. That's number 80. He's a liquid, and then you've also got bromine, and that's a liquid as well. Okay, everything else is a solid. All right. Types of properties and changes. So there's 2 types of properties and changes that we concern ourselves with. There's physical and chemical. Okay, physical changes and properties can be observed without changing the identity of the substance. Okay, so imagine you got a pot of water and you add heat to it until it boils. So it turns from a liquid water to gaseous water. Okay, liquid water to gaseous water. It's still water, still 2 hydrogens and oxygen combined. However, it's changed. This change is defined as a physical change. Okay, and it's the boiling point, or that temperature you had to get it at, is defined as the physical property of water. So the physical property of water is that it boils at 100 degrees Celsius. Okay, and the physical change itself is when it goes from liquid to gas. Okay, most physical changes are reversible, but there are some that are not reversible, like for example cutting your hair. Okay, cutting your hair, it's still hair, right? It's just 2 pieces instead of 1, but you can't really put that hair back together. It doesn't quite work the same. All right. So you've got other examples of properties of metals. Metals are shiny, diamonds are hard, higher boiling point, sugar dissolves. Now, so think about this real quick. If you have a cup of water and you take sugar and you stir it, dump it in your sugar, or you dump it in your water and you stir it up, the sugar dissolves, right? All that sugar is going to go away, and then you've just got a cup of sugar water. All right. If you leave that sugar water out long enough, all the water will evaporate, and what do you have left? Well, you still have the sugar. That lets you know that when that sugar dissolved, it did not get changed. It just dissolved. It's still sugar. Okay, so therefore, dissolving things is a physical change. Okay, and solubility is a physical property. Right? Chemicals changes and chemical properties are observed when a substance actually changes identity during a chemical change. So the big trick here to remember is that bonds are breaking and bonds are forming. All right. So if you actually took hydrogens and oxygens, if you take water and you run electricity through it, it's going to decompose into hydrogen gas and oxygen gas. Right? So you're actually going to go from having hydrogen and oxygen all bound together, making this water molecule, to 2 hydrogens and 2 oxygens bound together. Right? So that is a chemical property that water decomposes with electricity called electrolysis. Okay, so there's like if you take a piece of wood and you light it on fire, that's a chemical change. Right? You no longer have wood at the end. You have ash, which is primarily carbon, and then you have carbon dioxide that it formed. Okay, and you also have a little bit of water vapor that it formed. Okay, when iron rusts, that's a chemical change. You no longer have straight iron anymore. You have iron oxide. Vinegar and baking soda making carbon dioxide, and your stomach acid digesting food. These are all examples of chemical changes. Now, in a lab coming up, or one that you've already done, you had to identify, based on different things that you see, whether or not something is a chemical or a physical change. Okay, so here's a list of things that you want to watch out for to look for if it is a chemical reaction or not. The first one is if light is produced. Right? So if light is produced, you put two things together and it makes light on its own, then it is a chemical change. You can use that as a sign it's a chemical change. So think about like glow-in-the-dark fish. Okay, where they glow in the dark because there's a chemical reaction taking place inside of them, producing the bioluminescence. Okay, if there is a gas produced, this is also a sign of a chemical reaction. Now this one's a little tricky. Okay, so imagine you have a case of Diet Coke and you pour it really fast into a cup. Well, what happens? The Diet Coke gets poured in and it starts fizzing, and eventually it's going to flow over because you've fizzed up. Well, that looks like a gas is being produced, right? Not quite. Remember, Diet Coke tastes fizzy because it's carbonated. Carbonation is simply carbon dioxide that has been dissolved in the soda. Okay. Now, because that carbon dioxide was dissolved in the soda, when you pour it out, it's shaking that carbon dioxide loose so it comes out of the soda and it's no longer carbonated. Okay, but because remember we talked about before, dissolving something was a physical change, so therefore the opposite of it, releasing something from being dissolved, also has to be a physical change. Okay, so here's the trick when you're looking at gas being produced. If you take two different things and combine them together, okay, mix them together, and it makes a gas produced, then that is a sure sign it's a chemical reaction. So when you're using the gases produced thing, you always have to think about that. All right, where did that gas come from? Did it come, was it already present in one of the things I mixed? So think about that one, all right? So be careful. If there's a color change is a good sign there's a chemical reaction going on. For example, if you're standing out the sun, it's still August out there, and you go to the pool and you forget to put on sunscreen, the sun bakes you for a while, you come back home and you realize you're all red. Why are you red? Well, the sun's energy made a chemical change happen in your skin. It literally changed the chemical composition of your skin and gave you a burn. All right, so that's a color change. A heat change is also a form of chemical reaction, or a sign of a chemical reaction. So not that so you got to be careful. It's that if it does it on its own. So you take two things, you mix it together, feel the container it's in. If it feels warm, that means it's producing heat on its own and it's forming a chemical reaction. All right. Or vice versa, it could also be taking heat from you, in which case it feels cold. All right. And then finally, if it forms a precipitate. Precipitates are a solid that's formed from two aqueous solutions that are mixed together. So you start with two aqueous solutions, essentially liquids that have certain ions dissolved in them, okay? And then you mix them together. When they come together, they're going to form a precipitate. And a precipitate, it's kind of going to look like if you took a piece of, imagine you fill up your sink. Okay, but there was inside your sink, your bathroom sink, there was a little chunk of toothpaste that nobody bothered to wash away, and it just kind of sat there in the sink for a day or so, and it just kind of looks gunky and soft and blech, That's kind of what a precipitate looks like. And they can be all sorts of colors, all right? So those are the kind of things that you're looking out for signs of a chemical reaction. All right, so we talked about states of matter. We talked about signs of physical and chemical changes. We talked about how to use the periodic table to see if something's a solid, liquid, or gas. All right, do some of the practice problems. Let me know if you have any questions.